think I have to add one to your 56 on yours? Okay. So here's the idea that we're looking at. We're going to be given a rate of change of one quantity and asked to find the rate of change of another quantity. For example, if you blow up a balloon, you're changing its volume. But as you're changing its volume, you're also changing its surface area. And so you can figure out if the volume is changing at this speed, what is the surface area changing at a specific moment? Okay? And what we do is we use our skills in implicit differentiation and derivatives to figure this out. So we'll start off with, oh, my whole screen got interesting here. Let me just wait for it. There we go. Start with area problems. So here we have quantities changing. How fast is the area of a circle increasing? At the moment, its radius is 100 meters. So this is a pretty big circle. Okay? And the circle is getting bigger at a rate of 2 meters per minute. Its radius is changing. Okay? Now, if you think about that, that radius, it's not increasing very fast. So here's 1 meter. That would take 30 seconds to get there. 2 meters in a minute. As far as the numbers that are in this question, I can't really envision something increasing that slowly as a circle, but another example that would be similar is like if you dropped a rock in a still pond. When that rock hits the pond, a circle ripple goes out. And that ripple would be traveling at a certain speed, and so the area of that circle would be increasing as the ripple increases as well. So the key to these questions is, first of all, to understand that area is increasing with respect to time. So even though we don't know what the equation is, there is some function out there that says area is a function of time. There's also a function out there that says radius is a function of time. And you don't know what those equations are, but you know they exist because the area is increasing and the radius is increasing. Okay? Now, we want to find out the rate of change with respect of time for the area. This is our question mark. What do we know? We know the rate of change of the radius with respect to time is 2 meters per minute. In particular, we want to figure out the dA dt at the moment that the radius is 100 meters. So this is the setup. First of all, you have to acknowledge that area is a function of time, radius is a function of time, even though we don't know what those equations are. What we do know is there's a relationship in a circle between area and radius. That relationship is our area is equal to pi r squared. All right, I'm going to try to shut down Chrome. Thank you. Oh, I should do update attendance. No, I didn't close it. No, I didn't hit the X. I hovered the X. There's a difference. What's that? That time I hit the X. There we go. Let's see if that makes a difference for the speed of our program here. We know that area is equal to pi r squared. And so implicit differentiation says we can take the derivative with respect to time of this whole equation. And since a is a function of time, its derivative exists. Since r is a function of time, its derivative exists. How do we do the derivative with respect to t of the function a? Well, we would do the derivative of a is just 1 times by the chain rule. It'll just be the derivative. The derivative of a is dA dt. Just like the derivative of y is dy dx, if you were doing that with our regular variables. Now, on the right-hand side of our equation, how do you do the derivative of a power? Well, the power would come out in front, right? Subtract 1 from the exponent. And then since r is a function of time, the chain rule, implicit differentiation, would tell us we would need to multiply by dr dt. What was our question? We wanted to find dA dt at r equals 100. So now it's just a matter of taking the information that we have. R is at 100. We're told that dr dt is 2 in the question. Multiplying this all out, 400 pi, including our units. Area is measured in meters squared. Time is measured in minutes. So this circle, which is increasing at a rate of 2 meters per minute, its radius is increasing at that speed. At the moment it's at 100 meters, we know that its area is currently increasing at just over 1,200 meters squared per minute. Okay? So, yeah, I'm just, the only thing I can think of that big circular is like explosions that increase, although I don't think they travel that slow. The shadow. Could be. But wouldn't its shadow be decreasing as it gets? Depends on the person holding the flashlight on the asteroid as it's coming in, right? Wait a minute. Okay. We're going to do a little bit of imagination here. We're going to imagine the balloon is a perfect sphere, because we don't have formulas for balloons. So normally I ask you to, I haven't decided this year because I give you formulas in some things, whether or not you'll have to have your formulas memorized for spheres, and for cylinders, and for circles, and for squares, and for cubes. So the question is, does anyone know The surface area of a sphere formula. 4, oh, you're very close. Surface area.
I got one of them.
There's for a sphere, there's a volume formula and there's a surface area formula. And they're actually quite beautiful as far as formulas go. Okay? The volume formula of a sphere is 4/3 pi r cubed. And the surface area of a sphere is 4 pi r squared. And actually, I kind of visualize the surface area of a sphere this way. If you're looking at this golf ball from your direction, and you think of it, if you had to draw it on a piece of paper, what shape would you draw? A circle. Agreed? Like the shape that you would draw on a paper would be a circle. But on the paper, you would definitely not see the back side of the circle.
Depends how you draw the circle on paper. A lot of different projections.
Okay?
It's like the whole mapping issue.
So you would have a circle viewed from the front, a circle viewed from the back, but that would be two flat circles as if this was just a disk. In order to give it depth, you'd also have to imagine looking from the top and looking from the bottom, and putting all those together would give you 4 circles. So that's sort of the way that I visualize the surface area of a sphere, and it helps me remember the formula. I can visualize a circle from this side, a circle from this side. To give it depth, a circle from the top and a circle from the bottom. Okay? Which makes the surface area of a sphere 4 circles. Yes?
Can I make it mine 6 pi r squared because I also want to look at it from the sides?
But from the sides, you've already covered that from the top and the... Okay. Anyways. How is the volume formula related to the surface area formula?
Pi.
No. No.
Squared.
No.
The 3 from the r? It comes, wait. Come back to me.
Check this out.
Derivative. Derivative.
The derivative of the volume is the surface area. And they sort of, that's what, when you take a derivative of something, you move down a dimension, don't you? Like x cubed, the derivative becomes x squared. Volume is something cubed. The derivative becomes something squared. Does this happen with any other formulas you know? Oh, check this out. Area of a circle. Circumference of a circle.
Yeah, I saw that one.
Oh, moving down a dimension. Maybe, is that maybe just coincidence, or is it just kind of cool? I don't know. So, there's our volume formula. There's our surface area formula of a sphere. A balloon is 30 centimeters in diameter and being inflated such that its radius is increasing at a rate of 3 centimeters per second. So we know that radius is a function of time, and we've been told that dr dt is 3 centimeters per second. How fast is the surface area of the balloon increasing? So we know that surface area is a function of time, and we want to find the derivative of surface area with respect to time when at the diameter or the radius would be then 15. Since the question gave us the diameter. So here we have to figure out, is there a way that I can create a formula that relates surface area to radius? Well, we know for a circle, or for a sphere, sorry, that our surface area is 4 pi r squared. And now we can take this whole equation and do the derivative with respect to t. Again, we'd have to use implicit differentiation for this whole thing. Derivative of surface area is the derivative. But on the right-hand side, you have to use your power law, so the 2 would come out in front. And then implicit differentiation in the chain rule would say you'd also have to multiply by dr dt. So we can find ds over dt, plugging in the numbers that we have. Centimeters squared per, what was the unit? Seconds. This is the idea behind every single related rate problem. You have to recognize that things are functions of time, because that's important for implicit differentiation. You have to create a relationship or an equation between the variables that you're given, and then find the derivative.